right, everybody. So thank you for those that have come here, and thanks you for those at home. It's a real pleasure to have our second Perspective Seminar speaker, Dr. Anna Foeglein. I've known Anna for years, and she has known UQ for even longer than that. So UQ has known her. Anna has a PhD in analysis, right? So she's actually all the epsilon, delta, and probably much more, manifolds, a whole bunch of stuff like that. But since then, she's become one of the biggest names in discrete event simulation and simulation in general in Australia and in Brisbane, Southeast Queensland in Australia. And she'll tell us, I'm sure, about her industry experience in that. Very relevant for your project too. So the students are implementing a discrete event simulation themselves with quite a lot of events. Heap built in, but they learned about a heap yesterday. Yeah, but I'm looking forward to hearing Anna's talk, and let's welcome her, the ones here and the ones at home. Thank you.
Thank you, Yoni. Right, first step, technology. I'd say I'm not good at technology, but I'm the one who has to fix it all the time, so that's not going to fly. Right, so thank you for having me here and listening to me basically rant and rave about how much I like my job. Yeah, let's start at the beginning, which is, right, it's working after all. Right, so why would anyone do simulation? For me, it was pretty obvious early on. For the nerds among us, someone may recognize that C64 Commodore computer. My parents are both mathematicians who turned software developers. My mum got to bring home Hungary's first Commodore 64 over the Christmas holidays when I was 4. She made those little line faces fly across the screen. And I knew, this is what I want to do when I grow up. Obvious, line faces across screen. So I spent the next, say, 16 years playing, mostly simulation, like SimCity, Centurion, X-Wing. I'm really good still in an X-Wing, not so good in the gunboats. Age of Empires, also most of uni Age of Empires. Basically everything where you have something that's getting simulated, and then you try to make the best decisions and see what happens. But if something goes wrong, you just lose the game. For serious things, I ended up studying maths though, and I ended up being roped into pure maths. So I'm not sure if I can still understand / explain what I did, but basically it was called the Heisenberg Group. And it had to do with regularity theory. That's when you don't actually solve your differential equations. You just prove that there is a solution in some really weird space in which you maybe can't even take a derivative, which would be pretty important for a differential equation, right? So then you go and do massive, massive proofs with paper in landscape for the inequalities to prove that this solution is an actually useful function that is a solution. That's what we call regularity theory. And then you can start relaxing the assumptions on the space that you're in. For example, you can't just switch derivatives between direction if you're doing second derivatives. And that's what the Heisenberg group is. So as you can see, an incredibly applied and relevant thing. It was always a massive challenge to write grand applications with, and why would anyone not want to know this? But there is a lasting contribution that I made to the Uni of Erlangen, where I did my PhD. If you look closely on this little thing here on the picky, here's this complicated equation looking thing, right, with the fractal letters and stuff. So when they were looking for complicated looking maths for their marketing material, the maths and science faculty, that's from my thesis. And they still use it to this day. So lasting contributions in pure maths here. But then I moved to Australia for, let's call it personal reasons, also called having Joe Grotowski as my husband. So here's the conflict of interest declaration. But yeah, with these personal reasons, it turns out that when you are in the exact same field as someone at UQ, and it's a pure maths field, then it's really, really hard to get a job as a pure mathematician. And that's where it came in really handy that most of the time when I was doing my PhD and after that in the postdocs, I really didn't like getting up in the morning for the maths, but for making the grading system, for making the tutorials organizing system, you know, where the tutors would enter their grades and you'd calculate your arithmetic marks and mark who's absent and not. Well, that was fun to make. So I basically pretended that I'm better at programming than I am. And there was this wonderful company that's called the Simulation Group, who knew exactly what kind of person, the kind of mathematician who's trying to get out of academia is. That's because they were full of those people. And they basically said, okay, you like solving problems, you like playing computers, you like tinkering with coffee machines. Oh, and you like Star Wars, we're taking you. That was a quite fortuitous coincidence. And I actually looked at their ads back in Germany, thinking, oh, what a cool job. You're basically playing SimCity, except not in cities, but with big mining machines all day for a job. How good would it be to get a job at these guys? So yeah, that worked out well. So that's basically where I worked for 9 years, 2010-ish to 2019, when they got bought by Boston Consulting. And all of the nice maths PhDs, like 4 out of 6 people in the office had UQ maths PhDs, right? And then the other 2 people had physics PhDs from different unis. So we all were like, are we really going into big consulting? I personally said, no, I'm not going into big consulting. I don't want to move to Sydney for that in the first place. So instead of continuing with TSG, I kept working at a place called Integrated Logistics Company. I literally kept my desk because they were our biggest client here in Brisbane. They were like, who's going to continue our work? And I said, well, I could, for one, if you take me, and they took me. But on the other hand, there's this logo that you can't really see behind this little window there of AnyLogic. That's basically the simulation package that we've been using at TSG for most of the time. It's reasonably modern, it's reasonably good. And because they're very nice and responded to our bug reports and feature requests so quickly, we had a deal with them that, you know, TSG would sell AnyLogic software in Australia as, you know, the competent people. So when TSG suddenly disappeared, AnyLogic came to me and said, oh, could you please get an ABN and keep selling our stuff? And basically that's what I do in the remaining 20% of my time these days. So yeah, entrepreneurship, it happens sometimes just like that without even trying. And it's the scariest part of the entire undertaking, I have to say, talking to strangers who may or may not appreciate technical stuff. Really hard. All right, so let's get back to the simulation part of things. I wanted to talk today about why you do simulation and how you do simulation. Basically, simulation is the cop-out to OR, one could say, because equations are really hard to come up with when it's like, oh, let's describe a physical system, but how would the equations even work that describe how the system behaves? And what's even worse is, okay, and how do we solve them to know, you know, how to best do things, or what would be the end result, or something like that. At which point simulation just says, you know what, let's just see what happens. Let's you know, do it in little steps and see what happens in the end, and then maybe we can make sense of that. You know, let's just watch it play out. And people just use whatever tools are suitable for that. Like pen and paper, very popular. There are so many board games and you know, RPGs and stuff. Like tabletop gaming is pretty much a simulation that happens on paper and with some dice and in people's heads. Spreadsheets, very popular, especially in maths class. I have a soft spot for models that you actually build out of Lego or on a big table with little trains going around and that you can physically put together. Also very nice for teaching, it turns out. And I'll try to get this out of the way. But yeah, this picture is well, if you really wanted to, you could use an actual computer with an actual simulation package, you know, with specialized software to do simulation. And that's what I'm going to talk to a tiny bit next. Cool. Yeah, I'll try hard. All right, am I on camera now? Hopefully. Thank you, Yoni. Right, so people used traditionally for simulation whatever they could do in terms of maths and whatever their computers at the time could do. So in the 50s, that's where things kicked off really nicely. There was this dude called Jay Forrester. he was an engineer. I think he was at MIT. Massive contribution, as in one of the first usable types of digital memory for computers, as opposed to vacuum tubes. Like, really clever guy. But then he turned his cleverness to the business school and decided that he's going to explain to General Electric how it works, where, you know, if you first let your suppliers die off, then it's really hard to get them back and producing big time when you need them. Otherwise known as the bullwhip effect. He basically described it with a few differential equations of stocks and flows. And because people are super scared of numbers, but they like drawings, he drew them up in this kind of diagram that you see there. It's called a systems dynamics diagram. It's really just a graphical representation of differential equations. But you can feed those differential equations into a computer, even one at that time that may or may not have vacuum tubes in it, and get a solution. Hooray, simulation is born. So this took off like anything, because finally we can make complicated systems. People were trying to simulate like the entire world, including pollution and quality of life and population growth and education and whatnot. And there are several games doing this. There are really cool videos from the late 70s showing people in lab coats on big computers simulating the entire world. It's hilarious. But yeah, this is basically a really nice way of simulating things, as long as you just want to understand the general dynamics of something. As long as, you know, individual properties, if they average out, because you've got a big population of things going on and everyone sort of on average behaves the same, things work really well. This is how COVID gets modeled for the government in large parts. So, you know, still popular. It's really nice until you realize, okay, but maybe we want to capture the inhomogeneity. Maybe we want to capture the exact thing where things don't quite behave according to a nice smooth equations, like, you know, jumps, discontinuities, the exact things that these differential equations are not great at. So that's when people started to come up with the next version of how could I simulate. It's the part for the people who don't really like calculus. Again, that can I just write down my process and make it play out instead of having to put it into an equation? And that's where this guy called Jeffrey Gordon came up in the 60s with a process-based language. He basically said, let's take a flow chart of a process and translate this into a program. How bad can this be? Basically, anything that's a process, well, what's it going to do? It's going to take one quantity and then increase it and decrease it in every step, and, you know, increase or decrease another quantity accordingly. You know, like I don't know, I'm like putting papers from left to right. Well, the stash on the left is getting smaller, the stash on the right is getting bigger. I might have 7 people putting the papers from the left to the right, and then they need different times for that. Discrete event simulation, as I think you are doing this in class, right? That's the exact idea. And he came up with this first simulation language, GPSS, in the 60s. It's pretty straightforward. It's just code and there's a simulation clock. The discreteness of the events is really contained in the idea that you have a model clock and you have the model state really only change on specific ticks of that clock. In between, nothing interesting happens. You just evaluate the state of the model on clock ticks. If you know, oh, okay, I'm going to run out of material in 5 minutes, then you schedule yourself for a clock tick in 5 minutes to then reevaluate, okay, now my pile is empty. What am I going to do? Recalculate kind of things. That's a discrete eventness of things. Pretty much at the same time, and slightly by coincidence, people also invented object orientation as a concept while they were at it, because they thought, oh, wait, but the objects that I'm processing, they might have their own properties, they might have their own things that they contain. This idea came up with Algol 69 and then sank straight away because the computers weren't strong enough for that. Whereas the process blocks were really easy to, you know, understand and use and put into the code of the time, and it took off. And people, if you say discrete event simulation, will imagine something like this, that you have some kind of flowchart drawn up, and there's going to be servers and queues and capacities and delays, and maybe there are going to be conditions in which you decide which way you're going in your process, but it's going to be this kind of graphical process. And the hope is, and at least what the commercial vendors are all trying to tell you is that, oh yeah, and then you just plug your blocks together and whatever process you've got, it's just gonna work. And I assume that you're all up to the point where you're realizing already that this is not great, because anytime there's something worth modeling, complicated enough to be worth modeling, there's also going to be custom decisions for which in some kind of programming language, someone is going to have to describe the rules. in a slightly iffy way. But that's why most of these simulation packages also come with a more or less custom or more or less general type of programming language that then the experts can use to input more complicated and less graphical code. This kind of simulation, it's very practical, useful, easy to learn. You basically describe your process, you see the outcomes. There's all kinds of nice graphical results representation usually built in. And you can really do things like, okay, what if I have a random component happening, like, you know, rolling the dice for, I don't know, weather, stuff breaking, people going on leave, something like that in your process, and see how much variability you've got, which is one of the main uses of simulation when you're going like, okay, I'm not sure what the outcome is going to be, and especially what's my worst case, what's my best case, what's my typical case of things. So this was quite popular, is still quite popular. But then there's the stuff that, for example, Zoltan does with the swarms of birds, flocks of birds, swarms of fish, things like that, that instead of coming from a perspective of having rules that then govern little things that go through a path prescribed by the rules, you've got individual things called agents. Imagine them like, I don't know, like a whole big group of ants. And all of those ants has a rich inner life and makes its own decisions about what's it going to do. This thing here, for example, is called the Schelling segregation model, where you have basically a grid of agents, and each agent every like, you know, time step makes a decision of looking around, oh, are the other agents that are around me directly the same color as I am? Because if yes, then I'm happy and I'm staying here. But if not, then I'm going to move somewhere, you know, random other spot on the map that's free. And turns out that from this reasonably simple rule that doesn't even have a proper directedness of, oh, but where am I going to move? You still have emergent behavior at the end where a random pattern of, you know, pretty evenly distributed blue and red dots will coalesce into a fairly separate pattern of patches. And this kind of simulation is quite nice to explain a lot of things that are basically chaotic, where you don't have a set of rules that govern everyone together in a coordinated fashion, but everyone has their own little rule set. So like, you know, swarms of fish or bacteria when they do their chemotaxis, or very nice example, the zombies that you've got in a wonderful Cornell paper. You should really look that up. It's called You Can Run, You Can Hide. It basically explores what happens if you have a zombie disease outbreak based on US population density and pretty good estimates on how fast zombies travel. Where are you safest from the outbreak and how fast will it spread? Amazing model. And it's really nicely implemented as well in JavaScript, and it still runs at a decent clip, right? And inside your browser. And it brings together all kinds of wonderful mathematical models for, you know, how do I deal with chemical reactions? How do I deal with like, what's it called? Like small amounts of weird stuff in large homogeneous amounts of normal stuff that you don't want to model because too expensive computationally. Really, really good model. You should look at it. Anyway, the nice thing about agent-based modeling is that you can really capture the emergent behavior. The medium part is that it's kind of expensive computationally, but these days that's not a problem. Like we've got computers, and being sensible at the implementation usually helps. The tricky bit is that once you've got emergent behavior, now you're back to, right, but why did this happen? Like, yes, I saw this happen, but why and how would I influence this? So now you're back from being able to understand through making things play out to observing quite naively how things play out and then having to make sense of it. There's then the idea of why are we constraining ourselves to paradigms like this? Like, you know, great history lesson, everything fine, but we could actually combine all of these concepts. And that's what modern approaches to simulation do. You have individual agents that have their own little behavior, that pass messages between each other. But then you might also have rule sets because, you know, your typical business, for example, yes, you might have your staff who go and leave, who have breaks, who may or may not be motivated, who may be differently qualified, all of these individual properties, but they are part of a big process where you want to quantify how they, I don't know, process their workload or how they work through things or how they drive the machinery, right? And the machinery itself might be different agents that breaks down, things like that. So basically different kinds of models that capture whatever you're modeling from the perspective that's most suited to that particular module and part of what you're looking at. It's called hybrid modeling, and it's really not rocket science, but it's a big buzzword. So, you know, it's good to have heard about it. So there's the whole idea with, you know, while we're at it, why not integrate this kind of thing with GIS? Why not integrate this kind of thing with data exchange and visualization tools? And why not run this whole thing in the cloud? And therefore we can do lots and lots of parallel running. So, you know, it's all this wonderful digital twin and generally messianic representation of how wonderful simulation can be. In practice, it's not quite there. But, you know, in principle, let's just say it's not the technical possibilities that constrain the benefits of simulation in real life. So despite the fact that I happen to sell AnyLogic, let's just point out that you don't have to pay a single dollar to do pretty professional simulation. There's a massive market or, you know, just generally space of simulation software out there where you don't have to implement your own event calendar because someone has already done that for you, probably in a really good way. And there are different amounts of, you know, nerd factor to them. So there are things that are, for example, purely code-based. SimPy, for one, is free. It's good. It's quite similar in concept to SLX, which is basically the, like, if you wanted to ask me the nerdiest and coolest of simulation languages ever, SLX is it. It's purely code-based. It's not quite object-oriented, but object-based. It's like it favors composition, very much of an inheritance. It's been written by a guy who basically had massive, massive competence in how do I write a good event calendar? How do I do simulation useful data structures like sets that you can search really well, like maps that are really suited to the typical simulation task. He was called Jim Hendrickson, unfortunately died 2 years ago. So we'll see how this works out with SLX in the long run. But yeah, if you're a Cody person, then SimPy is the free thing, and SLX is the pro expensive thing. There are more graphical solutions to things. For example, JamSim, that's a Java-based simulator, and it's free. Used to be done by, I think, AECOM, and then they made it open source. There's MATLAB and Simulink. I used to have a MATLAB and Simulink poster on my bedroom wall when I was 15. So it's cute. It makes nice pictures. It's also $4,000 per package, so pretty expensive so far. But then you look at the prices of the specialized simulation software, like I don't know, FlexSim and AnyLogic and Arena and whatever they're all called, and those price tags are horrible. So, you know, don't go there if you're not PhD. There are learning versions if you need to learn them from a job. All of these expensive packages, they want to lure people in at universities. So you'll either see a free for students version or a free for personal use version. If anyone ever in a job ad goes like, you need to know this simulation tool, yeah, just go on the manufacturer's webpage. They're going to have a free version to download and learn. And they're probably going to have tutorials too, because they know it's hard to lure in people with expensive tools. All right, let's get into slightly more practical lands. What do I do for 80% of my work? It's slightly embarrassing to admit, but it has to do a lot with coal, in particular the Central Queensland kind of it. In a nutshell, basically, when you dig up coal and have to pay royalties on it, you don't have a particularly big vested interest in you know, being efficient about this, saving money on this thing called demurrage, which is when you have to pay a lot of extra rent for the ship that you're going to ship the coal on to your customer because you were so slow that it was there for 2 more weeks, for example, in the port, as opposed to when you ordered it for. Because the way that the contracts are set up means that these costs mostly come out of the royalties that you'd have to pay anyway. So while the manufacturers of coal, like the producers, are not particularly invested in this whole efficiency business, the state of Queensland, for example, very much is, because it's all our, it's all our money that is being thrown out of the window there. And that's why for the Central Queensland coal producers, about 10, 15 years ago, there was a push to, yes, let's have a coordination authority, or at least a coordination helper, which is called the Integrated Logistics Company, that's going to help the massive number of stakeholders in that system not waste taxpayers' money, basically. And it's a reasonably complex system, right? Like you've got, originally, you have 2 terminals there, like at Mackay, tiny bit south of Mackay. You've got about 300-400 kilometers of track going inland, heaps of mines that have these loadouts, they're called. It's like basically big hoppers that you put coal in on top, and the train goes up through under, and then the coal falls into the train, and it's reasonably straightforward. And then the train goes all the way out to the terminal that's at the coast, and there's a thing called a dumper where the coal comes out of the train and is put on a pile. And then the coal sits around on a pile for a little while or a long while, depending how efficiently the entire place is run. At some point, it's then put onto a ship, and the ship brings it to the customer. So you're trying, as a logistics person, you're trying to optimize the system in that when you know, okay, that ship's going to come up on Wednesday, then you want all the coal that ship is going to take there on the ground on Wednesday, so you can put it straight on the ship, and it can turn around and go away, and you don't have to pay money because it had to wait around for 2 weeks at the port and could do nothing. Right. It's not entirely easy to do this. So at some point, there were like 83 ships waiting off the coast. Considering that there are like, berthing opportunities for, if you use everything, for 7 ships there at any given time, 83 is pretty bad, right? Technically, the port that we were looking at is called Dalrymple Bay, is rated to get 85 million tons per annum through. That's reasonably big, like the port next door that belongs to BHP is rated at like 55-ish. But the performance was, in the best case, 65 million tons per annum. And this is at the height of the coal boom, right? So it's not that there wasn't anyone to take the stuff. It was that they didn't manage to get their ducks in a row and actually do the logistics right. And there were heaps of theories of, oh, why is this happening? And do we need to give these people more subsidies? Do more trains need to put in? Who's to blame for this entire mess, basically? But, given the losses where taxpayer money, at some point Queensland said, okay, so either you sort it out yourselves or we're sorting you out. And Integrated Logistics Company is right, we're sorting out ourselves. So this is where TSG got brought in, as in, you guys, you're good at building models. So yeah, a model was built. In the meantime, while the model was built, people managed to complete the red bit of track that connects the entire system to another port, that's Abbott Point, right next to the Whitsundays. Not a great place for a port, right? It's like next to the reef and everything. But yeah, this makes everything even more complicated because suddenly trains are going in all directions and taking up space from each other. It's all a big mess. So a model was built, and oh look how beautiful! See that little white thing? It's like a train coming in, and you can see it going through the inloaders and dumping. Like on the right, it's a bit black, and on the left, the wagons are grey, and you can see the colorful piles and the machines moving around, and oh, how cute is this, right? Yeah, okay, so this is not that useful, this animation, right? Because to be honest, we could have, like the people at port at least, they can have this in real life with beautiful gleaming sea in the background and perfect Mackay sunshine almost every day, right? So they don't need a model for this, but you also can't read off a lot of this. Also, full admission, so this is done in a package called Arena. It's basically a log file of a model run, and that was put through the graphics package Unity to 3D animated. So like, this is cute. You can absolutely show this to a stakeholder and they go, oh, what a professional model. And that's, yeah, maybe not the best. Okay, so this is the iteration number 2. This is the not 10-year-old, but about 3-4-year-old version of same situation, but kind of better model, does more things in the background. This is an incredibly dorky and uncool animation as well, right? At least it's useful for debugging the model when we're wondering, what is going wrong again? Because you can see what the trains are, why the trains are going, what they have on themselves, and what the port is doing roughly. You could have the list of train jobs as well if you wanted to. But still, incredibly dorky animation. And who knows if it's useful, right? It's little boxes moving around. And when you look inside the whole thing, this is what it looks like. It's a bastardized Eclipse with lots of code, different kinds of code, a little bit of graphical things to lure the noobs in so that they think it's easy, which it's not. It's a pretty major software development project to keep a model that is quite big in an extendable and manageable state so that you can deal with scenarios and have the whole process of, oh, but I ran that specific scenario a year ago, and since then there've been a million model changes, and I've also updated data, but I want to go back to that exact scenario and want to rerun it, but with the current upgrades and bug fixes. Like keeping track of that kind of data and making a model like that, it's way more tedious than it seems at the outset. And that's why, in the end, it does boil down to a very, very software developer tool. But then, okay, so we've got a model and the clever people at TSG can drive it, and still not a minute shorter demurrage for anyone, because, and now what? It's not a solution to watch an animation. You've got a model and it does something, and then what do we do with the something? So in the case of the DBCT, it was fairly tedious and long and years long of in part scientific experimentation, in part political machinations to sort out what is happening with the system. In the end, it was reasonably straightforward and definitely outside the scope of this talk. But what we did was like different ways of visualizing the outcomes, looking at, hey, what kind of outcomes do we even want to measure in this model? There's things that you couldn't do in real life because, you know, things go wrong all the time in real life. Whereas in a model, you at least have them, you know, without the exceptional events happening, without the, oh yeah, but Jono decided not to follow the rules today type of things happening. At least you see how your rules are playing out and why they're playing out, and you can tweak them. And you don't have to wait a year to see what a year's worth of operation under the new rule set looks like. You know, what if I had 4 trains more? I don't know. Let's wait a year and buy 4 more trains in the process and see how we go, right? That's why we have a simulation model. So that simulation model then runs and gives you, depending on log level, somewhere between 200 kilobytes and 6 gigabytes of data per run. But you do at least 25 seeds, as in different random streams per scenario, because you want to be sure that it's not, you know, a train breaking down on 1st of January instead of 2nd January, making all the difference, right? So you get lots and lots of data, and you're trying to find out what is happening. So yeah, it's after the whole model build process comes the whole, oh no, I need to remember the statistics phase of things. It was incredibly disappointing, to be perfectly honest, on my first day at TSG. Like I imagine, you know how in TV series, you have these simulations like in the crime shows where you have the, oh, this is the angle at which the bullet came in, and then comes the dotted line, and oh, that person was at the window, and that's why they must have shot the victim or something. And you, okay, that's not quite what I expected, but I expected something better than a zip file with tabular data that makes literally no sense to me. Like the better files have headers. That's about the level of horribleness. And you look at the data and think like, what is this? And then you have not one of these, but 25 per scenario, and it all makes no sense. So there's a massive amount of wrangling in there. On the plus side, at least there are no transcription errors from people recording real data on paper and then typing it in. But that's the only thing to be said for it against historical data. So there's a massive amount of processing happening where you put your data, your output data, either through R or through Python or through Excel. Excel is a love-hate relationship. It is surprisingly good once you're good at it. but R is nicer. Anyway, so learning data wrangling tools and visualizations and coming up with how you want to visualize your data to make sense of it is a massive, massive part of this entire simulation thing. It's not stopped once you've got the model. It's just starting once you've got the model. And once you've managed to, okay, I at least can read what my model run said. This one model run said it takes 5 hours for the train to turn around instead of 2 hours because the other one had 2 hours. Okay. And then next step is the why. And that throws you back from stats class into actual science class, where you have to come up with the, right, what experiment am I going to run to answer a question that I had to come up with in the first place? Why am I only getting 65 million tons through instead of the 85 I was promised? That's not an experimentable question. But you look at, oh, these train turnaround times, they don't look good. Are they a result or are they a cause? Now let's try to figure some parameters which might influence the turnaround times or not, and see how things respond. There is a big creative component to this entire problem solving part, and that's the non-technical bit, where you're just trying to explore a system that you may or may not have a good understanding of, to see, okay, what are the levers, what can I pull, what will make a difference, what won't make a difference, and get a feel for the whole thing to be able to fix it. For anyone who likes to tinker, it's an amazing opportunity and really the most fun part of the process. It's also the part where you have to talk to people who actually know what they're doing, the subject matter experts, the so-called ones. And sometimes their intuition is amazing and helpful and gets you on the right track. And sometimes their intuition is not that great, but that part where you get to know a part of real world and actually get a feel for it. It's the part as in, when you go and try to win in Age of Empires. Now you know how your Mongols work, that the Mongol die have a really good shot rate, but how am I going to apply this so I can win against someone who has really good anti-archery armor? So this entire thing is, of course, also a very iterative thing. So what, you start experimenting in one direction, you see it's a dead end, but you've noticed something else, so you adapt your model. So these models, they grow and get more and more messy. But once you've figured out how your system works, suddenly your model is very reusable and recyclable. At ISC, we have, for example, a monthly forecast, which is done with the model. We basically take next year's worth of, okay, what is everyone going to sell? We're a neutral authority, you can tell us. What is everyone going to plan for maintenance, for their mines, for their port, for their trains, for their tracks, whatever. Let's smash this all together in the model, see what falls out. And if we see that, oh, right, so everyone wants to have their highest throughput in February, which is a month that's 10% shorter than every other month. Oh, and someone wants to do maintenance at the same time. And by the way, that's the rainy season in central Queensland, so that's when the tracks are going to be washed out. Maybe not. And basically bring everyone to the table in a sort of coordinated way and sort out the problems before they arise. Really practical, really important, and crank the handle with simulation, but every single month something comes up that makes it harder. I've just finished the report this morning, so be good for October. If someone wants to build a new piece of machinery, straight away, hey, do we need this? How big does it have to be? Does it need to be able to stack or just to reclaim? Should we make it able to directly load onto a ship or not, or just to the piles? Things like that. Before you build one of these things, they're like in the millions and millions. It's really good to try it out on a computer, even just for a feel. And same thing with, oh, what if we split up our yard across instead of lengthwise? Also, a lot better to experiment in a computer than in a way that you can actually be held liable for by the people who are paying contracts to use your terminal and then go all, hey, what are you doing with my code? So yeah, it's useful. It's basically ongoing, at least if you write the model well, and if you understand your system, at that point, it at least becomes the gift that keeps on giving. So let's just recap this and get a bit more abstract again for a moment. So why did we do the simulation thing? because it makes experiments cheap and fast, because sometimes you need to experiment with a system to understand it, because it's just too complicated to simply optimize, as in, chuck in a solver, out comes a solution. And whatever you're planning to experiment on and to ask in terms of questions, that informs what you build as a model, and it's going to go back and forth. And this is the moment where I'm going to shamelessly rip off this is how we do good simulation questions from my lovely colleague, Andrew Kramer, also UQ PhD in maths. Did it with Tony here. Good place. As in, how do we ask good questions for simulation? It's called mathematizing. Anyone heard that word yet? Yeah. So if you're into math teaching and curriculum writing and stuff, mathematize is the activity of translating an intuitive concept into a mathematically tractable concept. A sensible thing, really. Good to have a word for. So when we're asking, why is my process not delivering the throughput I want? Well, it's a very legit question, but it's not going to be that good to answer, especially not with a simulation. Whereas if you transform that into, what's the net time cost of each of my process elements? At least it's a starting point to, okay, so where am I wasting my time? Or how do I design my reporting system to be robust? Very, very happy question or popular question with clients. How do I design my emergency department? How do I design this, that, factory floor, mine, whatever, expensive thing that you want to get right? Well, that's not going to be an answerable by simulation question. What you can do is, if my reporting system is like that, and this is the pattern of things coming up, is it going to get overwhelmed? And if yes, with what probability? Or if I have option A, B, and C to design it, what are their respective costs and robustness factors or whatever? But you can pick and choose between options. It's not going to design for you. You can test things that exist and have rules. And finally, the ever popular, who's to blame for this office being over budget? Who's to blame for us not delivering system capacity? Who's to blame for everyone paying demurrage? These things, it's not really going to answer this, because blame is a pretty moral concept. However, if we can pinpoint things, what part of this office is over-provisioned? Whose parameters improvement would help the entire system pick up its game? Things like that. These are testable questions. They're good for simulation. Basically, testability, quantifiability is the name of the game. And if we are then thinking about, oh, wait, but this is all connected to a business. So the things to keep in mind are, does my question link to a decision that needs to be made? If I can't do anything about something, there's no point in even simulating it. Does it link back to the organization's goals? Seems like the same as the first question, but it's not entirely, because if I need to make a decision, but it's not going to make a big dent in something I care about, again, why waste the time? The question needs to be bounded. We can't deliver world peace and maximal throughput at the same time. You have to pick one. Like, we need to know when we've answered the question, or at least given something that qualifies an answer. It needs to be specific, and it needs to be quantifiable, because on the inside, every simulation is just a big, big, fancy accounting sheet. We're going to add numbers, subtract numbers, divide numbers. In the end, it's going to be numbers. Experiment structures are, they're like in science, right? You have your input variables, and you start with a certain set, but you might extend them. But you're basically starting with the things that you want to probably change and see how the system responds. And then you wonder, okay, so what are my response variables? And this is also an ever-growing set usually. Typically, you go for something that's called a KPI, a key performance indicator, that you go, like, this is the thing that I'm caring about. This is why I'm asking the question in the first place. For example, how many pieces of paper can I process at any given time or over a day in this office? But then it turns out that, that's just an outcome, and you really want to see what is going wrong in the process. And then you are adding more and more levels of logging and measurement of what is happening inside your process. So that the response variables, it's like a set that grows from high level and important to low level and quantifying the bits that you think are going to make a difference and going to go wrong or right. But in the end, you get some kind of answer. And then it turns out that when you simulate things, you have to deal with the point that your answers aren't necessarily simple. Like, you know, the typical queuing system, for example, you get maximal throughput when you manage to choke feed. And you always like single server or double server systems, you only like, you know, if your servers always have something to do, you make sure that there's always something in the input buffer. They can work all the time. There's no downtime. Excellent. Right. But if I keep my input buffer filled, that means that if my servers ever go down for a moment, that queue is going to grow. And the things in the queue are going to wait. What's acceptable? What's unacceptable? So there's a trade-off between what kind of answer do I even think is good? And, you know, there's a point where I'm saying, okay, but for that extra ship that I'm putting through in a year, maybe I don't want to accept everyone waiting for an extra week. It's a trade-off, and it's really someone who knows what they want out of the system who has to determine what's an acceptable, unacceptable, and sweet spot type of solution. This is also where a lot of the public and, you know, high-level simulation ideas fall down. When you have someone with an emergency department saying, all right, I want to optimize my emergency department. That makes total and utter sense. Anyone who has ever waited for a doctor to see their broken ankle knows that. But then when you go like, okay, so what is a good emergency department really? Is it that the maximum wait time is no longer than whatever? Maximum wait time for things that, you know, could really hurt? Not a lot of people die in a year. The doctors are not completely overworked. There's a million things that you could see as good or not. And we haven't even talked about the fact that you don't have infinite money. So the part where deciding what is good, basically your objective function, is where the big can of worms start. And finally, last technical slide, I promise, model details when we implement. Now that's again, pretty double-edged sword, because when you want to capture something in proper amount of detail, okay, you want to capture all your control variables, you don't get away without those. Your output measures, you don't really get away without those. If you want to capture an important dynamic of your system, especially if it's easy to describe, yeah, you'd want to put that in. On the other hand, if it's really complicated and you could just, you know, cut a corner and approximate it with some random outliers, yeah, cut that corner. It's mostly a decision of, you know, what's worth it, what's not worth it. Building things modularly enough that once you decide that that corner can't be cut after all, you can substitute the cutting with the proper and fully modeled version of it. And then there comes the human factor. Oh, the important stakeholder really wants to see that thing modeled. There's always that one bugbear that people have with their system that they find important and tricky enough to pay money to simulate. For example, there's a bit point, that point. Oh, but if we have this train and it hasn't been stacked out perfectly, then to reclaim it back and put and dig the coal back up, it takes so long and it's so slow. And we were like, do you have to capture that in the model? And we were like, yep, sure, easy, we can do that. We have like, you know, we'll have a marker on the pile. Oh, good. Can you get us the data for that? You know, like how long does it take to reclaim a pile like that versus a good pile? Oh, we don't have records of that. So they're digging back through the records. They're giving us like this buttload of data. We're digging through it, basically going like, you know, you had maybe 3 piles in the last 2 years that were like really slow. Oh yeah, but that was when there was a massive storm. So the bugbear that, you know, people have because it really upset them at the time, it may not even be something that is worth capturing in the model. But if it's the project manager whose bugbear it is, you capture it. And then maybe deactivate the feature when they don't have the data for it. Same, so that gets us to the decrease model size. If things are really hard to make, that's when the corner cutting starts. If we don't have data to support something, That's when we can't say anything better than maybe like a statistical distribution based on historical data. Though people usually overestimate what kind of data they have, and you go and build your model in pretty great detail, and then you look at your data and the data that was promised, and you go like, but I can't drive this with this level of data. And then you're like, but we don't have anything better. And then you start, okay, how am I going to take my simple data and massage it into something seemingly complex that's not too wrong statistically to drive whatever I've built, and I'm really out of time now. That kind of thing, right? It happens. There's actually risk from complexity. If you build something that's really complex and has lots of little inputs that you have to get right, and you don't get them right, it can go egregiously wrong and just take off in a completely wrong direction with, you know, classic nonlinear dynamics. And you don't even notice it, and you don't have a feel for it. So when we don't know detail, pretending we know detail is a lot more, and then guessing parameters, it's a lot more dangerous than in the nice and obvious case of, oh, this is very simplified, let's guess something simplified. So complexity risk is always there, and it's one of the most popular ways of getting a calibration wrong. And finally, there's again the political part with, if we measure how many truck drivers we now need with the automated trucks, then the union is going to be really, really upset. Things like that. Or if certain optimization things for a certain rollout of a certain internet say, oh yeah, so the way we're going to do this to maximize the, you know, the efficiency of spending money and getting money back is, right, no poor person gets NBN, and the rich people get it first, and then they pay already for it, and we can pay for the next phase of rollout. Again, that's not something you can come up with as the end plan, that, you know, and the poor neighborhood, like in the middle of the city, nah, they're not getting it. So yeah, you know, there's always someone who is going to see a side in the modeling where you go, okay, so how do I do this in an honest way, but without getting the whole project sunk on the potential what it might say. A timely example for this whole detail question, last thing, COVID, right? So this is a very, very classic SIR model. It's super duper simple with stocks and flows and just not even compartments of people. And usually we go about the reproduction number, right? To see, okay, how long does it take for an infection to fizzle out, or to you know, everyone's got it at some point, however the dynamic will play out. There's this R0. And R0 is not necessarily something that you can really measure, especially with incomplete data. But let's say we sort of can, because, you know, we've at least seen how people, you know, we know this person and he gave it to 7 other people, and we saw this person and she gave it to 5 other people. Okay, let's go for an average of 6. But it's okay when you, as long as you have measured data. But then you go, okay, so if we shut down schools, what is that going to do to R0? If we shut down public transport, what's that going to do to R0? All of the things that basically rely on modeling in the first place to find out what the parameter value for this abstract thing has to be are very, very hard to capture when all you have is your abstract model. On the other hand, and that's what happened in Bangalore, for example, the local uni had amazing census data of where people live and how far they travel and where they go to work and where they go to school and stuff like that. And they built their own simulation engine in C++, because performance, because they wanted to model the entirety of Bangalore, basically going about their daily jobs on a more or less correct statistical basis, and having COVID and spreading it on reasonably easy experimentally determined parameters of how you transmit and how you come into contact with people. And then suddenly you get all of the super spreaders, and you get all of the, teachers meet lots of kids from like different parts of the city, whereas if everyone just stays in their local neighborhood, you might not get this kind of spread. And then you have the problem that I just mentioned, complexity risk. Cool, we've got this model that really captures the things that we are like the mechanics that we are trying to test, as in, you know, everyone stays in their local neighborhood, everyone only meets 3 people at a time, things like that. But do I have my parameters right enough that the outcome of the emergent behavior is better than what I would get out of a simple set of ODEs? And it's not entirely sure. And to make it worse, you only know after. The part where you go validate is only happening once you've got your historical data. So the entire, how do I know that my model is saying the right thing? It's a really problematic part of the process. So these are the questions that we've gone through. When should we simulate if we have a process? You know, concrete questions. Will this lad work? What option is best? Where's my bottlenecks? I have an idea. Will it do what I expect? Let's not simulate when there's no process, when there's no rules, where people just make decisions off the top of their heads, where you have no information, where you don't need to simulate because you can calculate on the back of an envelope, or if really needed with an Excel spreadsheet. Or when stuff happens that doesn't happen on the regular and it's super custom anyway. Right, that was the filler project, in case I needed more to say, but I don't. So finally, let's just wrap up with, so why do simulation? Well, for me, it's because I like the maths and the programming. I like the thinking and the learning about different kinds of things. I never knew I'd learn so much about how to store trains. I never knew I'd learn so much about, did you know coal can go off? Did you know it spontaneously combusts? It really does. You have it sit around in a not well ventilated space for a bit and it goes on fire all by itself, and it's really hard to put out too. Things like that. How emergency departments are staffed, how that you really don't want to go in dialysis because the management of it is like, oh my God, all kinds of things about highly relevant things around you. You learn just by people asking you to simulate it. And finally, big shout out to the people I work with. Most people, at least in the simulation and generally OR space, are super nice. A bunch of them you'll probably know from here UQ, at least if you're staying here in the Brisbane or, you know, Australia area. The rest of them is going to be like at QUT and the other unis. Most of them also hang out at Urban Climb or at the various crags. So yeah, it's a surprisingly small world and everyone knows everyone, but in a nice way. Okay, thank you very much for listening to me and sorry for going over time.
Make sure I'm in the mic, so sorry.
Oops.
So we probably have some questions. Yes.
This is the moment when we need to chat. Except if people here have questions.
Yes. So.
It's a pretty even mix. So what do I do day to day? Client interaction? Yes, definitely, because every time someone asks a question, at some point the answer will have to be delivered. And you have to talk with your client about the exact question as well. They don't usually come up with a question in a form that lends itself to being answered. You want to specify what's going on. And even if their question is completely specific, you usually want to confirm some details of the data. So client interaction definitely happens almost every day. The programming part, that's an it depends. So if you are at the beginning of a project, then absolutely, because you still have to get, most of the time you have to get whatever logic you're doing into your model or build an entirely new model or extend an existing one. After that, a bunch of the time is like, okay, now I've got my output data, but I'm looking at some different aspect than I did before. So you'll have the whole programming bit of the data processing. Okay, more scripting, but still you end up usually, even in Excel, you end up in the VBA and otherwise you end up in the depths of R and tidyr. So you have the programming component. And then there is I'm looking at this chart and I think it's telling me something, but I have no idea what it's telling me. Experimentation thing, that's like maybe 30% of the time. It's quite a healthy mix. If you're at a bigger company, you can specialize more in them. So there are, you know, the people that you push in front of the clients because they can summarize things really well. And then there are the people who really don't want to talk to clients because they're shy and they like to program and they don't like to talk to people. And if you have a medium-sized company, then you can find your niche that way.
Questions, thoughts for the people at home as well? So
right.
Yeah, Anna managed also to put a shout out for Urban Climb, I assume, so you can find her there if you climb, or you'll see her probably more around the School of Math and Physics. And let's thank Anna once again. This was wonderful. Thank you.
Thank you. Yeah, but you'll also find Amy there. She's a lot better than me.